Hi all, today we will see how we can simulate single phase full bridge converter with various loads using MATLAB. So for that purpose we want a PC. In order to do what is the average and RMS values, we want to calculate on the MATLAB software. So a single phase full bridge rectifier, you can do it for different loads. What are the different loads means we can do for R type of load, RE, RLE, RL load with freewheeling diode, RLE load with freewheeling diodes. And depending on L value, we will have two types of modes. What are those two? Continuous mode and discontinuous mode. So the source we are going to take it as 230 sin omega t. Frequency we are taking it as 50 Hz. So in continuous conduction mode, we will take the load as R equal to 10. If L is there, L is 30 millihenry. If E is there, we will take it as 30 volts. To have continuous conduction mode, let's alpha equal to 30 degrees. If one cycle is 2 pi and if the frequency is 50 Hz, its time will be 20 milliseconds. So if 360 degrees is 20 milliseconds, 30 degrees is 1.66. Same way is continuous conduction. If R equal to 10 ohms, L will be 10 millihenry, E is 30 volts. And in same way, if 360 degrees is 20 milliseconds, then 60 degrees will be 3.33 milliseconds. In the same way, if 360 degrees is 20 milliseconds, then 180 degrees is 10 milliseconds. These things you need to remember, and we will do it. So we want to simulate it for 3 cycles. So one cycle is 20 milliseconds, 3 cycles means 60 milliseconds, like this. So in MATLAB, the location of the blocks are like this. So these are the blocks which we are going to use: power guide, single phase voltage source, ground, current measurement, voltage measurement, diode, thyristor. From block go to MUX, RLC series branch, scope, display, RMS block, mean block, divide block, in order to calculate form factor and all. So this is the circuit diagram of a single phase rectifier. So this is the MATLAB diagram which we are going to use. These are some of the waveforms that we will get for R load, for RE load, for RL load discontinuous conduction, for RLE load discontinuous conduction, RL load continuous, RLE load continuous, RL load freewheeling diode continuous conduction. So continuous conduction, you can see the current is not zero, it is continuous. RLE load freewheeling diode. If freewheeling diode is there, voltage can't go negative. Okay. So continuous conduction. RL load discontinuous conduction with freewheeling diode. RLE load discontinuous conduction with freewheeling diode. So this part, the current in L is not damped yet. So here it is 0. After that the current in inductor is 0. So it is going to E, like that. So these things you can observe after drawing the circuit in MATLAB. So what are the different components required for us? We want current measurement, voltage measurement, AC voltage source. These are the from blocks. These are gate pulses, and these are the thyristors we are going to use. This is RLC series branch. This is DC voltage source. Again, current measurement. Here some MUX is there, scope is there, RMS calculating block, mean calculating block, that is average calculating block. You can see the value in the displays. So these things we are going to connect now. So you open MATLAB. So this is MATLAB library. So this is MATLAB work environment to connect blocks. So they will have many block systems. Among them we will be using Simulink, and in Simscape there is something called Sim Power Systems. They are specialized technology. Only these two, specialized technology and Simulink. So these two we are going to use. So from specialized technology, what are the different blocks required for us? First one, to work with any of the block within this, power guy is must. So place power guy. Next, in power electronics we want a diode and we want a thyristor. So we don't want detailed thyristor which will have holding current and all those things. We just want a thyristor. Next, go back. From measurement, we want current measurement, we want voltage measurement. Machines, nothing, interface, no. Elements. From elements, we can take ground or we don't, whatever it is. See this RLC branch. So here you can see. This branch itself is R, this itself is RL, this itself is C, this itself is RLC, like that. Whatever you want, you double click and you choose it. If you double click it, you can choose. Okay, go back. Electrical sources. So AC voltage, so single phase AC supply. Next, for E load, DC voltage source. Go back. Next, in control and measurement block, in measurements, we will collect that RMS and mean block. RMS, mean block. These two. Next, this is over. From here, I think we have collected all the blocks that are required. Next, we will go to Simulink. So in Simulink, there is something called sources. From there, we can collect a constant block. Next, we can collect pulse generator. That's all. Next, from sinks, we want a scope, we want a display. Next, you go to signal routing. There we want a mux. Then we want from. Then we want go to. So we have collected, I think we have collected all the blocks that are required to construct single phase full bridge rectifier. So I would like to write the name. Full bridge rectifier. Now we will connect the blocks. First, what we want a AC voltage source. So the name is very large, so make it small. So just VS or V in. Next, we want 4 thyristors, so rotate it. So I don't want this measurement and all, so I can remove it. So measurement, so you untick it and apply. I want this number circuit and I want this to be near to idealness. So putting 2 zeros there. Here also I would like to put 2 zeros. So I don't want inductance. So forward voltage I reduced it. Number circuit is there. Simply apply and OK. This is the block. Let the name of the thyristor be T1. I want 4 such thyristors. T1, T2, T3, T4. Now you connect the thyristors in order to form the bridge. Now we will connect it, voltage source. So this is a rectifier, not inverter. So we will connect it here. Next we will connect load. So its name is also large. We will make it small. LOAD. Load. We connect the load. So this is E. If you want, you can connect it initially and make it 0. If you don't want it, E. Delete and you connect it. Move aside. E is coming. So this is a single phase full bridge rectifier. So what is the purpose of this diode? If you want to introduce a freewheeling diode, we will introduce that diode there. So if you want a freewheeling diode, this diode will be placed there. For diode also, I don't want this measurement block. So measurement apply. I want it to be near idealness. Place 2 zeros there. Here also you place 2 zeros. Apply. Okay. Change the name. So this is freewheeling diode FD. So if you want, you connect it. Excuse me. Now what we want to do measuring. So to do measuring, so measurement of voltage will be done by voltage measurement. So yes. Source current measurement. So you remove this wire and current measurement is done in series. So you must connect it in series. Yes. Sorry. Okay. This is source current, source voltage. Next I want load current and load voltage. So you press control and then you can copy this and place it here. Then leave control. Let this be V0. Next I want to see load current. So delete it. Control, right click and place it here. And this is to be connected in series. Yes. Now I want to see the waveforms. Waveform can be seen in block called scope. This is the scope. So in this scope, in the single scope, I want to see what is Vs, what is Is, what is I0, and what is V0. So totally I want to see 4 waveforms. So if you open it, you can see it is having only one axis, but I want 4 such axes. So go to setting, and you can set it as 4 axes, 4, and apply and OK. Now you can see there are 4 axes. Okay. So I want to connect it in such a way that the first one is Vs, next I want to see V0, next I want to see Is, okay, I0, next I want to see Is. So I want to connect it like this. Scope. So V0 and I0, they can be connected here like this. V0, I0. So Vs, you bring it like this. Vs, and this is Is. So all this wiring seems to be confusing. So which wire is connected to which one and all these things. So to remove this confusion, we will do wireless signal transmission by using from and go to. How they can be used means, see. Now I am removing this Is and I am removing this Vs. These two I will connect by using from and go to blocks. So you bring this from and go to. So see. So this is a Vs signal. This must go to some other place. So you connect it to go to. So go to, you give a name, some VSS like this. The same tag, VSS same tag must be there in from block to receive the signal. So this is the from block. It is also having, let us say, VSS. Okay. So this seems to be large. So you can reduce the size. And this from block. So this Vs is go to through this and it is received from here. And as this is receiving that Vs, you can connect this here. Okay, like this. Now Vs will go here and from there it is directly transferred to from and it will enter inside. So in the same way you can connect Is also. So control and copy it. And let the name be ISS. Where is from? Okay, control and copy. Change the name to ISS. Apply. Okay, and you can connect it here. This one also you connect it here. So IS will go into this and from there it will come here and it will enter into the scope so that we can visualize the waveforms. Next, we want to calculate RMS and average values for V0 output voltage, let us say. So simply you bring the RMS, you bring the mean, and you connect the displays. So this will give you average value. This will display you sorry, this will display you V RMS value, this will display you V average value. So what is the purpose of these two, we will see. Next, gating signals. So when T1 must on, T2 must on, when T3 must on, T4 must on, that we will see. So move it back. This is so. Let the namings be Z1, G2, Z3, Z4 like that. G1. So I want 4 of such kind. So control and you drag like this: G1, G2, G3, G4. Okay. So G1 is T1, T2. So if you see waveform of a single phase rectifier, how it will be, I will draw it roughly. This you can see it here. So let us say this is a sine waveform. So during the positive half cycle, here the triggering is done for T1 and T2. Next, in the negative half cycle, here triggering is done for T3 and T4. Okay, that means this is alpha triggering. This is pi plus alpha triggering. So first of all, I want to show you this continuous conduction. For that purpose, what is alpha means 30 degrees. That is the time you need to set is 1.66 milliseconds. 1.66 milliseconds. So in place of alpha, you want to place it as 1.66 milliseconds. Pi plus alpha means 10 milliseconds plus 1.66, that is 11.66 milliseconds. So in settings for T1 and T2, the phase delay is 1.66 milliseconds. For T3 and T4, the phase delay is 11.66 milliseconds. Okay. You minimize this. So here we need to set these things. G1, G2, G3, G4. So I connected. Now we need to set the settings for gates. So what is G1? So usually the gatings are given through microcontrollers whose output voltage is 5 volts or 3.33. So let us say I am giving 5 volts amplitude. What is the period? The period is same as the output cycles, that is this one, which is of 50 Hz, that is 20 milliseconds. 20 milliseconds. 20 e minus 3 milliseconds. Next, what is the pulse width? The pulse width is, so for the thyristor to get triggered, you must give the pulse width so that the load current is just greater than the latching current. So let it be some 20% by the time latching current comes, let us say. Next, phase delay that we have seen just now. So as this is gate G1, for gate G1 it is 1.66 milliseconds. So 1.66 milliseconds, E minus 3. Apply. Okay. The same way for G2 also. Same. 5, 20 milliseconds. Pulse width, let it be 20%. Phase delay 1.66 milliseconds. So for G3, so amplitude is 5, period is same 20 milliseconds, pulse width 20%, but the phase delay is, as this is G3 G4, it is 11.66 milliseconds. 11.66 milliseconds, E minus 3. For G4 also same, 5, period is 20 E minus 3, pulse width 20, phase delay 11.66 milliseconds. Apply. Next, what is the supply peak? So we need to set all the values. So source voltage is 230 volts. Frequency 50 Hz. Phase delay, there is no phase delay, so we don't want any measurements. Apply. Okay, that is the Vin. Next we want to set these values. So we want just R and L, so we can set it as RL. So the resistance is 10, the inductance is, so we have taken it as 30. So here you can see R is 10, L is 30. E, if you want E also, we will set it as 30. If you want to do for RL only, make E as 0. Apply. Okay. So for now I want to see only RL, so make E as 0. So V not RMS or everything is set. Now we will run. So we want to see only 3 cycles. So 0.06. That is 6 milliseconds. So you save it somewhere. So I'm saving it as some name. Now you run it. So this is the average value, this is the RMS value. If you open the scopes and auto scale this, so that you can see the waveforms like this. So this is the source current, which is having harmonics, it is not sinusoidal. This is the load current, which is having ripple, but actually we want it to be DC, pure DC. So this is also having some ripple, which we want it to be pure DC. So here you can see, as L is there, after 0 also there is some current flow. So the voltage is negative. Okay. So this 0. So to see this 0 line, what we can do is we can apply some constant as 0 by using a mux. So I will show it for Vs, we can do it for V0 and all. Simply bring this mux and you connect it here. You connect a constant with 0. And you connect it here. You save, and if you run, now you can see the 0 can be seen here by a line. Same way you can connect it for V0 also. So now you can change the load accordingly and you can see the different waveforms.